Welcome to the next lecture in the TYC Materials Modelling course. I'm Dorothy Duffy. I'm Emeritus Professor of Physics at UCL, and the topic of the lecture is Classical Interatomic Potentials. The aim of the lecture is to give you an overview of interatomic potentials appropriate for a broad class of materials and to help you make an informed choice of the interatomic potentials appropriate for your project. So the lecture is recorded in 3 parts, and there are detailed notes to accompany the recordings. In the first part, I'll give you an overview of the advantages and the limitations of classical potentials. I'll explain what I mean by physics-based potentials and how this relates to bonding, and then we'll go into the simplest of all types of potentials, two-body potentials. I'll introduce a case study, which that is phase transitions in ferroelectric crystals, but I'll really go into this in more detail in the tutorial in a couple of weeks' time. In the second part, I'll introduce more complicated interatomic potentials, those multi-body potentials that are used for organic molecules and biomolecules, and also a different type of potentials that are used for metals, that is actually many-body potentials, and also the potentials that are appropriate for covalent solids, such as carbon and silicon. In the third part, we'll describe the most complicated potentials that we have, the React-SF potentials. And these are particularly relevant to chemical interactions where bond breaking and bond forming are an important part of the process that you want to simulate. We'll finish by choosing potentials and give you a summary of the overall course. So first of all, why use interatomic potentials? We know that quantum methods, so it's DFT, are very powerful and they're really quite accurate. So why do we want to neglect the quantum properties by using classical methods? Well, of course, the obvious answer is that these methods are orders of magnitude more efficient in terms of length and time scales. And so they went. Of course, there are limitations. I like to quote the famous statistician George E.P. Box, who said, "All models are wrong, but some are useful. And you should always be wary of this, no matter what type of modelling method you're using." Also, these potentials have been fit to quite specific calculations or else experimental measurements, and you must be wary of using them outside the range of which they're actually appropriate for. There's no information about the electronic structure, so that means they're not appropriate for any simulations in which the band structure electropic properties are required. Nevertheless, some systems and processes still remain inaccessible to quantum methods. They require large length scales or large time scales. So examples of things that require large length scales are dilute alloys, which you need a very large unit cell. The same is true for disordered materials or complex surfaces, particularly absorbents and surfaces. If you want to go to the dilute limit, you obviously need very large unit cells. Some types of defects, grain boundaries, dislocations, domain walls, also have very large length scales. So in order to model these appropriately, you need very large unit cells inaccessible to DFT. The same is actually true for large time scales. Processes such as diffusion, fracture, thermal conductivity all need very large time scales, nanoscales, nanoseconds, or perhaps even microseconds. If you want to calculate accurate free energy surfaces, then the methods such as metadynamics need very large time scales in order to converge, so these potentials are appropriate for these methods quite often. So interatomic potentials are generally physics-based. That means that they aim to encode the quantum mechanics of bonding into the functional forms that are used in order to model the interactions. So as undergraduates, we're taught that there are 4 types of bonding: ionic, covalent, metallic, and secondary bonding, which can either be van der Waals or hydrogen bonding. So from a material science perspective, the classification of material is done in terms of the bonding, because this is what actually dominates the properties. So the classes of material are ceramics, which are ionically or covalently bonded, and these are associated with very strong bonds and very large bond energies. So consequently, they have high melting temperatures, they're very stiff, and most of all, they're brittle. So if you hit them with a hammer, they'll shatter into thousands of pieces. Metals, on the other hand, of course, are dominated by metallic bonding. They tend to have slightly lower bond energies, so maybe lower melting temperatures and not quite as stiff. But most of all, what's associated with metallic bonding or metals is that they're ductile. So you drop them or you make a car out of them and you have a car crash. They bend, they don't shatter. Polymers have a mixture of two types of bonds. Within the molecule, there are covalent bonds. Between the molecules, there are secondary, weaker bonds, such as van der Waals or hydrogen bonding. So they tend to have lower melting points. They're not as stiff. They can be ductile and they can be brittle. And this, whether they're ductile or brittle, will depend on the proportion of the covalent bonding in the material. If they're very heavily covalent bonded, you will get a brittle polymer. So the message is actually that the properties of the material are clearly captured by the bonding. Therefore, we want to actually describe the bonding, whatever type of bonding we have in the material, very accurately with our interatomic potentials, and then hopefully we will capture the properties. Well, the simplest of all types of interatomic potentials are the two-body potential. That basically means that we can express the cohesive energy as the sum of the interaction energy between all the pairs of atoms in the materials. I'm going to discuss three types of two-body potentials. Lennard-Jones potential, which is appropriate for interaction between molecules, either in gases or in polymers and biomolecules. The Morse potential, which describes the covalent bonds in small molecules. And the Buckingham potential, which is appropriate for ionic crystals. So first of all, the Lennard-Jones potential, which I'm sure you're all familiar with from undergraduate days, which is used for interaction between gas molecules and the interaction between molecules in polymers or biomaterials. So the functional form has got a sum of two terms, an attractive r to the minus 6 term and a repulsive r to the minus 12 term. The attractive term is r to the minus 6 describes the dipole-dipole interaction. These can either be induced dipoles or permanent dipoles of the molecule. And r to the minus 6 describes the decay of these interactions quite accurately. The repulsive term is described as r to the minus 12. Is supposed to represent the Pauli repulsion that comes into play when the atomic orbitals overlap. The r to the minus 12 functional form is actually not physically based. It was originally introduced for computational convenience because it was the square of the r to the minus 6. So it made the computational process much more efficient. There are two free parameters in the model. One is the epsilon term, which represents the depth of the well, or the bond strength, and the other one is the sigma parameter, which represents the atomic or molecule size. So a small sigma means that the atoms or molecules can come much closer together before this very strong repulsive wall comes into play. So the Lennard-Jones potential has been very successful and is still used for biomaterials. But it was originally introduced for materials modelling in the early 60s, where it was used to model liquid argon with great success. So the second two-body potential is the Morse potential, which is actually used for the covalent bonds in small molecules rather than in large molecules. So it has got three free parameters. The D term, the D subscript E term, is actually the dissociation energy of the molecule. So it measures the energy required to actually separate the two atoms or that involved in the bond. The R subscript E is the equilibrium bond length, which will show you the minimum separation, minimum energy separation. And the alpha term gives you the shape of the well, which is shows you how anharmonic it is. So all of these parameters can be fit to vibrational properties of the molecule. Therefore, we can get very accurate Morse potentials for small molecules. The third and final two-body interatomic potential that we're going to discuss is the Buckingham potential, which is appropriate for ionic crystals. The bonding ionic crystal is clearly dominated by the Coulomb interaction, and I guess we're all familiar with the form there. And basically, the charges on the ions I and J are represented either by formal charges, in this case it would be plus or minus 2 for magnesium oxide, or they can be partial charges, in which case they're generally fit to DFT calculations to work out what the appropriate charge for the ions would be. But in addition to the Coulomb interaction, we need to describe the overlap of the atomic orbitals, like the Pauli repulsion, and also the polarized dipole-dipole interaction. So for the dipole-dipole interaction, we have an R to minus 6 term, similar to the Lennard-Jones potential. But for the Pauli exclusion, we actually use an exponential term. In this case, there are two parameters, as we can see, A and rho in the equation. And this actually gives you a bit more flexibility in terms of fitting, and it's more realistic in terms of what the repulsion looks like in terms of the functional form. But you must be wary of, if you plot the Buckingham potential, it shows you a graph which, instead of going off to plus infinity at very short distances, it plunges down to minus infinity. Clearly this is unphysical, and you must be wary of this if you're using a Buckingham potential. Generally, it doesn't really come into play, because if you start your simulation off near the bottom of the well, in equilibrium position, then it doesn't cross the barrier and you never see the effect of the strong attractive interaction. But if you start with it, if you have a very strongly non-equilibrium system, it is possible that it will cross this barrier and your simulation will fail catastrophically. So the ions in an ionic crystal are intrinsically polarizable. So when you apply an electric field, the nucleus goes in one direction and the electron goes in the other direction. So you get a dipole moment induced. And this is actually important for some properties, particularly dynamic properties, such as phonons and diffusion. So the polarization plays a vital role in these properties. So if you want to model them, the polarization must be included in the model. And this is generally achieved by use of the shell model. So in the shell model, you have a core and a shell, and you assign a positive charge to the core, representing the nucleus, and a negative charge to the shell, representing the electrons. And these are attached via a spring with the spring constant K. So the charges and the spring constant are all fit to the dielectric constant, or the polarizability of the material. And this actually is a very good way of representing some types of material with high dielectric constants. You don't always need to use these for ionic crystals. It depends on the properties that you want to actually model. Classical modeling of ionic crystals is a very long, successful history, and many complex materials and processes have been modeled very successfully. One example is the ferroelectric PZT. So ferroelectric material is one which has got a permanent dipole moment even without an applied electric field. So PZT is a particularly interesting property because it's got a very high piezoelectric effect, which means it's very good in terms of sensors and transducers. So it's an alloy between its lead, zirconium, titanium oxide alloy. So it's got a very complex crystal structure, which varies according to the amount of zirconium or titanium in the crystal. And as you see from the phase diagram shown here, if you actually got just pure zirconium, then you get a rhombohedral crystal structure. And as you increase the amount of titanium in the crystal, it goes through different crystal phases, ending up at pure titanium as a tetragonal crystal structure. Round about the 50% mark is where the most interesting properties are attained. This is called the morphoproprietary boundary. So you can see, because it's an alloy, in order to model this, you actually need very large unit cells, and it's inappropriate to use density functional theory or the quantum methods. So it's important to get a very accurate interatomic potential in order to describe this material. And this has been recently done. It uses the standard Buckingham potential and shell model in order to capture the important properties. So we're going to describe this in a bit more detail in the tutorial next week, and so I won't say anything more about it here, but it's just to demonstrate that actually these very complicated materials can be modelled using this very simple bucking potential. So when we're modelling mixed materials such as alloys, we don't always have all the potentials we need. So it's possible we're modelling an A-B alloy and we know what the potential is between A and B, but not between B and B. In which case we can sometimes use something called mixing rules in order to derive the unknown potentials. The most famous and commonly used ones are the Lorentz-Berthelot mixing rules. So these are used for Lennard-Jones potentials. So for instance, if we know the potential between A and B, we can calculate epsilon AB from using the geometric mean of EAA and epsilon BB on the arithmetic mean of the sigma term. So these are actually widely used for organic molecules still, because if we have a large organic molecule, we don't have all the interaction between all the atoms in the molecule. There are equivalent methods for the bucking potential, but they're really not often used, and it's not advisable. If you have so few atoms in the crystal, it's better to actually derive more potentials than use mixing rules, which are probably not very accurate. So the message is for these, use with care, but they are appropriate for organic molecules and quite successful. So that comes to the end of our two-body potential summary. So the message is that if we use carefully parameterized potentials, we can model very complex materials and phenomena. They're very efficient for ionic crystals, and you can use multi-million atoms and nanosecond simulations. We can model complex materials and large-scale features and defects, and also long time-scale processes. So that comes to the end of the first recording. The next recording will move on to many-body and multi-body potentials that we use for different types of materials.